In this video, we're going to start talking about our last operation between functions that we'll consider in this course. We've looked at how to differentiate sums and differences of functions. We use the product rule to differentiate products of functions. We use the quotient rule to differentiate quotients of functions. Now what we're going to do is use the chain rule to differentiate composition of functions. First, though, we're going to give a quick recap of composition and really what I'm going to call decomposition of functions, breaking those things apart to see what the pieces are. Then we'll talk about the chain rule intuitively, give a nice little explanation of what it means before we move on to other videos where we'll give the proof of the chain rule and some examples of how to use it. So here's our quick recap of composition. Say we have two functions. The composition of those two functions, we'll read this as f composed with g of x, is really f of g of x, where g of x is the input of our f function. The domain of f composed with g is the x values in the domain of g, where g of x is in the domain of f. So here's our picture that we have. We have these three sets. We have our x values, our g of x values, and then f of g of x. And what we do is we take all these points here and we bring them over to points in this g of x set using our g function. And then what we do is we take these points and we bring them over to our f of g of x set using our f function. But what we'll notice is that we really only can take the x values that give us outputs of g that will work as inputs of f. So that's what we mean in this second point. Another thing to note is that composition is not commutative. F composed with g of x is not the same thing as g composed with f of x in general. It's like subtraction and division, where the order really does matter. For addition and multiplication, order doesn't matter. We can multiply or add things in whatever order we'd like, and it's always the same. For composition, that's not necessarily true. Here's a quick example where we can just practice composition of two functions, right? We can take a look at f composed with g of x, or if you'd rather, you can call it f of g of x. And similarly, we can look at g composed with f of x, or really g of f of x. So go ahead, pause the video, take a look at each of these, and hopefully we'll be able to see how these are different, but how they feel pretty similar, and just give us a quick little reminder about composition. Pause the video and come back when you're ready. Okay, so for this first example in blue, we're going to take this g of x function, and we're going to go ahead and evaluate it inside of our f function, which means we're going to be putting it right in there. So this is what this will look like. We'll call this a square root of g of x minus 3. But we know what g of x is. It's x squared plus 1. So this is really a square root of x squared plus 1 minus 3, which we can call x squared minus 2. We can't simplify this function anymore, so we'll just leave it like that. Similarly, for g of f of x, we're going to be taking this f of x function and putting it inside of g. So we'll really have, instead of x squared plus 1, it's going to be f of x squared plus 1. But we know what f of x is. That's the square root of x minus 3. So we'll square that and add 1, and that's going to give us x minus 3 plus 1, which is x minus 2. So you'll notice these are a little bit different from each other because of those differences in the order of composition that we had. Hopefully that's a helpful little reminder. What we're going to care about, though, is decomposition of these functions, because think about the product and the quotient rule. When we were differentiating products of functions, the first thing that we asked is, what are the pieces here? What are the two functions that we're multiplying? Now we can find the derivative of each of those parts, and we'll put them together in the way that the product rule specifies. We did the same thing with the quotient rule. What are the two functions that we're dividing here? What are the derivatives of each of those parts? And now we'll put things together in the way that the quotient rule specifies. So for the chain rule, we're really going to be forced to think about these functions that are compositions as two separate pieces composed together. And so we want to make sure we know how to identify the pieces. It's a little bit trickier sometimes than identifying products and quotients. So let's take a look at a couple of examples here. We want to write out each of the following functions as a composition of f and g, where g is on the inside of f of x. So these are two separate examples, right? We can draw a nice line right down the middle. We'll consider these things separately, but what we want to do is to come up with options for, maybe I'll put g of x here first, and f of x, where this is the inside function, and this one here is the outside function. And we'll do the same thing for this. We'll come up with some options there. What we'll notice is that we're not going to get unique answers, meaning there are multiple different options of ways that we can decompose this into two functions. So that's going to be a little bit tricky. So pause the video, take a moment to see if you can figure out what's going on with these, get some options, and then we'll come back and talk about them all together. All right, maybe you're back. If not, go ahead and pause it again and try and do these. But one of the, I don't want to say obvious answers, but maybe one of the most common ones that we'll get in examples like this is to say that this 4x squared plus pi, all of this stuff here, is the inside function. And now once we highlight it, you can see it's inside of the sine function. So we'll say it's inside of sine of x. Cool. There are other options that we can do, though. What you could notice is that we could highlight just the 4x squared. We could say 4x squared is on the inside of sine of x plus pi. It's like a phase-shifted sine function. And we can compose 4x squared inside of that. You could also just say x squared is the inside piece composed inside of sine of 4x plus pi. And you'll notice that in each of these, if we take these g of x functions and put them in for x, we're going to get this y equals sine of 4x squared plus pi. There's some silly examples that you could do. You could say like x is going to get composed inside of sine of 4x squared plus pi. We call this like a trivial composition because it's not really doing anything, right? You're just taking this identity function and composing it inside. There's no big deal there. We'll stay away from those. What we'll notice is that this first one seems to be both the most common answer I get from students when I do this face-to-face or when I interact with students individually. This is the first thing that students mostly see, not all the time, but a lot. But that's going to be really helpful because it's going to be probably the way that we'll do things for the chain rule. In this next example, there's probably not a super common, basic, intuitive one. There's probably two different versions that people will do. Sometimes people will look at this exponential e to the x squared plus 5 as the inside piece, and they'll say all of this stuff is underneath that square root, right? So there's our square root function. Other times, people will just look at the exponential part itself. The x squared part itself. This is a really common one too. We could look at just the exponential itself in just a second. And this would be composed inside of e to the x plus 5. These are the two ones that I see a lot of, and then this one comes next, where we can again do like a little shift on the inside of that square root function and compose in our e to the x squared. This one we don't have like this one kind of dominating option. We kind of have two of them, and that's because you can think of this as having multiple layers of composition, right? You could see that this x squared is inside of our exponential, but then this exponential stuff is inside of a square root. So again, there's kind of like multiple layers of composition that we can see here. That's probably a bad way of visualizing it, but whatever. Hopefully we can see that. All right, so this is how we're going to identify pieces. We will build up some good intuition for how to identify the inside pieces nicely. I don't want to say correctly. I want to say nicely, because there's, again, multiple different ways that you can identify pieces like this, but some of them will work better than others initially. The nice part is that for most part, our intuition will be really good. Okay, so let's put this stuff together and see if we can talk about differentiating composed functions. So here's our problem. if we have different layers of composition, we could rewrite this with a little change of variables where we basically say, grab all the inside stuff here and just call that U. Or whatever else you want. And so we've got this U equals G of X. Sometimes people will use T's. Doesn't really matter. We're probably used to using U's and V's because that's what we normally use with the product and quotient rule. The issue here, though, is that we're likely interested in dy over dx or the derivative d over dx of this big composition of functions. But if we write that with our change of variables, then this is the derivative d over dx of f of u. And the question is, what's the problem here? It's right here. The function that we have is written in terms of a different variable than the way that we're differentiating it. So we want to see how does this function change with regard to x, but what we have is a rule for what our function is doing with regard to u. That's the problem. We have to come up with a way of linking these things together. And what we'll do is we'll investigate that visually. So here's what we're going to be looking at. I'm going to pull up a little animation of some gears that we have. So we've got 3 gears connected in a row. We've got some motor turning gear A. Gear A is turning the red gear B, and then by them being linked together, that's turning gear C. So we have these 3 gears that are linked together turning each other. We can just look at these things and observe rates of change here. What I mean is we can answer the question dc over dB. We could say, how many times does C revolve around in the time it takes gear B to revolve around once? What's the rate of change, or you could think of like a speed, in relation to gear B? So let's just watch. We can see the dots are going to link up together. So we'll just count the revolutions that the blue gear makes in the time it takes for the red gear to do one whole revolution. So we'll start now. And there's our revolution. Okay, so we got to follow that point on gear C to see where it ended up. Here, we'll start it. It only goes about halfway around. So what we'll notice is that gear C spins half a revolution in the time it takes gear B to spin one. Now what we're going to do is the same thing, but we'll look at the red gear B and the green gear A. So again, we can see the dots are going to link up, and we have to count the number of revolutions the red gear is going to make in the time it takes the green gear A to go all the way around. So get ready to start counting. Here we go. So that's 1 revolution, 2 revolutions, 3 revolutions, 4. All right, so that means gear B we could think of as it's revolving 4 times as fast, right? That kind of speed is being multiplied by 4-ish. Cool. Okay, so what does that mean now? What that means is that we can find the rate of change of gear C with regard to gear A, right? We can go back here and take this half and 4. So we'll say, all right, half, 4, and let's just follow the logic of what we're trying to find. We're trying to figure out the number of revolutions C is going to make in the time it takes A to do 1. And we know that when A spins once, B spins 4 times. And when B spins once, C spins half a time. So doesn't it make sense that we're really just multiplying these things together? And we could say, oh, okay, that means C is going to spin 2 times when A spins once. And you can kind of count that, right? We can notice that when the green dot is over here, the blue dot will be on the bottom. And now we can count the revolutions. 1, 2. There we go. 2 revolutions. So this is what the chain rule says. The chain rule says that if we want to link rates of change together, we can just multiply through, we say the chain rule, because we have this kind of linkage of related rates of change. So that's how the chain rule works. Now what we could do is use this to say, like, okay, if we know that gear A is being turned at a speed of 15 revolutions a minute from whatever motor it is turning, then we can find the rate of change of C, the speed of C, because we know, again, that dc over dA is 2, so C is turning at 2 times 15, 30 RPM. Easy enough. Cool. All right, so a quick little summary. What we have to do now. Remember our dilemma. We said that if we were interested in dy over dx, we need to find a way of differentiating d over dx of f of u. Well, what we're going to do is we're going to link those things together by looking at the rate of change of u with regard to x, right? Just like here, we said that dc over dA was equal to, I should have written this the other way around. We'll do it this way. Half times 4. That's dc over dB times dB over dA. That's what our chain rule is going to say. For y equals f of u, that's differentiable at u equals g of x, and u equals g of x is differentiable at x, so basically everything is differentiable where it needs to be. The composite function is differentiable at x with the derivative of y being dy over du times du over dx. The derivative of y with regard to this intermediate variable u multiplied by the derivative of u with regard to x. That's our link. That's what the chain rule says. In our next video, we'll prove this, and then we'll do a little bit of work using this and actually applying it. This is what the chain rule says, though, and that's the intuitive explanation of it. Hopefully that's helpful as we're moving forward.